Hi, welcome to the screencast for electrolytic cells. So a voltaic cell that we talked about in 9.4 is a spontaneous redox reaction that's going on to generate electricity, and you separate it into two half cells so that the electrons have to travel through a wire or generate electricity to complete the redox reaction. An electrolytic cell does just the opposite. It uses electricity to force a non-spontaneous or a redox reaction that won't naturally occur on its own to happen. So basically you're forcing the reverse reaction to happen. So components of an electrolytic cell, fairly similar to a voltaic cell, except now you need a power source, which has to be a battery or a DC source, so the electrons are only flowing one direction. You have to have the electrolyte, so instead of having two half cells, you have an ionic compound with both positive and negative ions all in one cell. You have to have electrodes to conduct the electricity. And so the electricity is going to be conducted from the battery into the electrolyte to cause the redox to happen. One will be oxidized, one will be reduced, and then you need wires to connect the whole thing. So here's a picture of what an electrolytic cell could look like. So you see the electrolytes in there, and you've got negative anions. Those should be metals because metals are going to tend to, the anion should be a nonmetal because they're going to tend to lose electrons to become stable. You're going to have cations, which are going to be positive ions and most likely a metal. And so then you're going to have the positive end of the power source hooked up to one end, and that's going to attract the anions or the nonmetal. They're going to move over there, give up their electrons, so be oxidized. So we call that the anode, and it has a positive charge. And then over on the cathode is where the negative charge is flowing, or the electrons are flowing, which means the positive metal ions will flow toward that to pick up the electrons and become solid metals. So typically you'll have a gas produced at the anode as the nonmetal becomes a diatomic gas and is oxidized, and you'll have a solid metal being reduced and precipitating out at the cathode. So in this case, if you had NaCl, the Cl ions would go to the anode and produce chloride gas, and the Na ions would flow to the cathode and precipitate out as sodium metal. And this is why salt water corrodes metals, is because if you have any two metals at all, so for example, the Statue of Liberty is copper plated, or is copper on the outside, and it's attached with metal rivets to an iron shell or to an iron skeleton inside. And then they put it in this big salty area. They put it on an island out in the middle of the ocean. And so all that salt water with two different metals basically formed an electrolytic cell, you know, when there was mist and stuff in the air. So it wasn't a big surprise when all of a sudden those rivets started corroding off and the whole copper shell started sagging off. So you're probably too young to remember, but they had a huge restoration project of that. But same thing goes on with your car. You've got more than one type of metal on it. When you get the salty snow on it, so you've got salt water on there, you get an electrolytic cell forming and creating rust. So then, just summarizing again on this slide, it's the reverse of a voltaic cell. So in a voltaic cell, redox generates electricity, and instead in an electrolytic cell, electricity is forcing redox to occur. The anode and cathode charges seem to be reversed from a voltaic cell. And I should just include it, that's the charges. And it's not seems, they are reversed, but same process is happening. The anode electrons are still being released, so it's still oxidation, but now it's at the positive terminal. And the cathode is still where reduction occurs, but the electrons are flowing over there to reduce the metal, so it's considered the negative terminal. And that really wraps up electrolytic cells.